Right, so once again, good morning. So
Morning,
can
sir.
you guys see my screen now?
Yes, sir.
All right. So do you guys have any question or concerns regarding with our last module?
Yan naman po, sir.
All right. So if there's no questions, then let's now start with our module 4. So as you can see, our topic for today is relation. Okay. So to those who are already done with Math 100, so this is actually like a deeper or another topics when it comes to relations. Okay, so most of the topics in here are already part of the Math 100. So this one is already super easy to understand for you. Okay, so first, what is the meaning of relation? So as you can see, we will only be able to build a relations once we have two sets. Okay, so we cannot have a relation if there is only one. Okay, so that is why we call that one relation. So if you're going to take a look on this one, we have two sets. Let's say set of x and then set y. So to have or to build a relation, so let's say one factor is to make or to have a Cartesian product, okay, via combining those two, okay. So to get all of the possible relations, we will use Cartesian product, wherein you'll just simply multiply all of the elements of your x and then all of the elements of your y. Okay. So in Cartesian product, this x is mostly called the domain. Okay. So take note on that one. And then for the y, we call this one range. Or sometimes we call this one codomain. Okay. So domain for the x and then range for the y or codomain. So it's the set of all ordered pairs x, y. Okay. So you guys already know what is Cartesian product. It's just simply multiplying the first coordinates to the second coordinates. Okay. So whatever is your first coordinate, that is your domain, and then whatever is your second coordinate, that will be your range. Okay. So as you can see in Cartesian product, arrangement matters. Okay. So here's your first coordinate. Here's your second coordinate. Okay. And then whatever is the elements of your x, that is your first, and then whatever is the elements of your y, that is the second coordinate. Okay. So x is an element of set x, and then y is an element of set y. So in symbols, you can write this one in this kind of manner. Okay. So it is in a set such that element x, y is an element of x and elements of set y. Okay. Same with this one. So the first element x of the ordered pair is related to the second element y of the ordered pair. So we call this one binary relation. Okay. So each set, okay, having a first coordinate and second coordinate, we call that one binary relation. So from the word binary, we have two coordinates or we have two elements on that relation. Okay. All right. So what is this binary relation? So it is a relation R from a set X to a set Y is a subset of the Cartesian product X times Y if element X, Y is an element of R. Okay. So you can denote this one as X R Y. Okay. So this X R Y is just the same with this X Y is an element of R. So in here, we're just saying that this X Y is in relation or an element of relation. Okay. So the same with this one, meaning x is related to y. Okay, or x is in relation with y. Okay, meaning we have a certain relation. Okay, but of course, before we could say that they are in relation, so we should take a look on what are the requirements to check before you can see that they are in relation. Like for example, they are related by blood, they are related by friends only. They are related as a co-worker. So we have a lot of kind of relations like lover, enemies, and so on and so forth. Okay. So that's one thing that you need to check before you can say that they are in relation with each other. Okay. So in here, we have the student and then the course. So Bill is actually related with Comsci, meaning maybe uh, the course of Bill is Comsci. That is what he is taking right now. Okay. And then Mary is related with math, maybe because this is his course that he is taking right now. And then the same with this one, Bill is another, or again, related with art. So you could say that uh, Bill has two courses that he is taking uh, consecutively. Okay, so he's taking comp sci, and at the same time he's taking art. Okay, and then Beth is taking history and then taking comp sci at the same time. Okay, and Dave is related with math. So that's the relation. Okay, so you could say that each one of them has one course or two course. Okay, so that's their relation. So let's have another more example when it comes to relation for you to understand this one. So with the table, we can derive relation as Bill is related with ComSci. So basically, we just put it inside a set wherein each call this one each binary relation, okay, contains two coordinates or two elements. Okay, so of course the first one is the x or the domain, and then the second one is the range. Okay, so this one came from our table. Okay, so Bill comes I, Mary Matt, Bill Art, and so on and so forth. So this one now is in a form of a set, okay, or set relation. Okay, thus we could say that uh, bet history is in relation with R, or bet R history, or again bet R is in related with history. Okay, so where this one came from? It came from this part. So at the same time, you can say that Bill is related with ComSci or Bill R ComSci, and so on and so forth. So you can do that on all of those examples. Okay, or binary relation. So are we clear so far on how did we come up with this kind of relation set or set relation?
Yes, sir.
Yes, sir.
Okay,
Yes,
all
sir.
right. So this one is actually self-explanatory already. Anyway, so this is like a bonus already. So you're going to have a seat break, which is very similar with this one. So we have four tables wherein you need to come up with an ordered pair, okay, or binary relation, just like this. Okay. And then we have the number five, which is the opposite of this one. So you have to come up with a table. So from binary relation into a table. Okay. So are we good so far for the secret number one?
Yes, sir.
Yes, sir.
All right. So let's now move on to the harder topic, which is relation using graph. Actually, this one is not harder. Uh, Still easy. Okay. So we have two sets in here, let x and then let y. So x contains an element of 1, 2, 3, and then y contains an element of a, b, c, d. So you can define this one using a Cartesian product.
Mm.
No. Sorry. This one not came from a Cartesian product. Okay, so this just a random relation that came from those two sets. Okay, so we have here 1a, 1b, 2a, 2b, and then 2c. Okay, if you're going to get the relation using Cartesian product, you will have you'll arrive at 12 total of relations. But in here we only have 1, 2, 3, 4, 5. Okay, so those are just random, okay, relation that came from our sets. Okay, so in here we just want to show that this relation can be shown using a graph or this one. Okay, so we have this y coordinates and then x coordinates. So as you can see, the x coordinates is our domain, which is the first one, which is 1, 2, 3, and then the y coordinates is our range, which is this one, a, b, c, d, which is labeled as you can see on our presentation. Okay, so what we want to do here is to plot, okay, each relation on our graph. So as you can see, we have 1a, then we have to plot it in here. So we have 1a, 1b, 2a, 2b, and then 2c. And all of those are in relation or a set of relation. Okay, so this one is an example by showing this set relation into a graph. Right, so let's talk about the main range of relation. So as I mentioned a while ago, all of the elements under X or your X axis, which is this one, okay? The horizontal line is your domain, and then all of the elements of your y or your range is your y or range of your y is your range, okay? Which is this one, okay? So all of the elements of x is your domain, and then all of the elements of y is your range, okay? So again, right here we have the domain and then the range. So this one came from, is it the same with this one? Man, this one came from nothing. Okay, this is just an example. Okay, this one is just an example of a domain and then a range. Okay, so this one is our x, and then this one is our y. All right. So let's have another example. So using the table before. So from here, we could already see that the domains are Bill, Mary, Bill, Beth, Dave. Okay, and then the range is comp sci math, art, history, comp sci math. But then again, since it's in a form of set, okay, so it should be only distinct and of course no repeated uh, values or element. Okay, so as you can see, we have two bills and then we have two bed. Okay, but since it's in the form of a set, then we have to remove the repeated element. Okay, so in here we could say that the domain are Bill, Mary, Beth, and Dave only. And then for the range, we also have four because comp sci is repeated, and then math is also repeated. So you have to remove the repeated elements. So we have only uh, come up with four range and then four domains. Okay, so are we clear so far up to this point?
Yes, sir. Yes,
Yes,
sir.
sir.
Right, so again, if you guys have a question, so feel free to ask me anytime. Okay. Okay, so let's have another example. So we have set x and then set y. So set x containing 2, 3, 4 elements, and then set y containing 3, 4, 5, 6, 7 elements. So we have here a question, and then its condition. Okay, so define a relation R from x to y. So this is one very important keywords that you need to take a look or check every time. So we have here from x to y. So take note from x to y. Okay, so x first before y. So if this one is from y to x, then you should start with y followed by x. Okay, that is your first condition to form a relation. Okay, so thus we can say that xy is an element of R if x divides y, having zero remainder. So in here we have another condition wherein for us to be able to build a relation or a binary relation, we should follow or we should come up wherein x divides y having a zero remainder. Okay, so as you can see, there's no solution in here. Okay, so I would like you guys to analyze this one, okay, on how to come up with a certain relation using this condition. Okay, x divides y. So my only question is this x divided by y or y divided by x? Anyone from the class? Is this x divided by y or y divided by x?
I think x divided by y.
Mm-hmm.
X divided by y.
X divided by y. How
That's
about
what
the
I
Sir,
think.
y
others?
divided by x. Sir, y divided by x.
Y divided by x. So the correct answer is y divided by x. Okay. So don't get confused on this one. X divides y, meaning your x is going to divide the y. Okay. So meaning your x is the divisor. Okay. So don't get confused on this one. It doesn't mean that it's x divided by y. Okay. All right. So let's answer this one. So let's see what are the possible relations that we can come up using this condition. All right, so again, we have here y divided by x, okay, and then it should have a remainder of 0, okay, really say even, okay, because if it's even, then we don't have a remainder. Okay, so y divided by x, so 3 divided by 2, okay, so are we going to have a remainder if it's 3 divided by 2?
Yes, sir, meron po.
There is. So 3 divided by 2 is not included in our relation anymore. How about 3 divided by 3?
Pwede, sir.
So since we have, or we don't have a remainder in that one, and we have an even result, which is 1, so we can list that one as our first relation. So how about 3 divided by 4?
Di pwede, sir.
So no, so we will not list that one. So 4 divided by 2?
Pwede, sir.
Possible. Okay, so we have to list here these coordinates. How about 4 divided by 3?
Di pwede, sir.
No. How about 4 divided by 4?
Pwede, sir.
Okay. So as you can see, all we need to do is follow this condition, okay? Up to the last case. It's like distributing everything from this side to that side, and then this side to that side, okay? So FOIL method. So 3, 2, 3, 3, 3, 4, 4, 2, 4, 3, 4, 4, 5, 2,
Excuse me,
5.
sir.
Yes?
Are we writing y for x before x or x before y?
Y first, Y. Okay, Y divided by, sorry. X first before the Y, okay? So my mistake. Okay, this one should be 3, 3, 2, 4. 2, 4. So thank you for that one, Mr. Walawewa. And 4, 4. Yeah. Okay. So X first, followed by the Y. Okay. But when it comes to the second condition, we have to follow this format. Okay, Y divided by X. Okay. So how about 5 divided by 2, 5 divided by 3, and then 5 divided by 4? Is there an element or coordinates that wherein it's equal to even or having a remainder of 0?
None, sir.
None, right? How about 6? What are those elements?
3 and 6, sir.
2 and 3.
2,
2 and
6, 3,
6.
6.
And then 3 and 6. Okay.
Yeah.
How about 7?
None.
None.
None, right? Okay. All of them will give you a remainder. Okay. So as you can see right here, we form 1, 2, 3, 4, 5 relations. Okay. So yeah, this is now our answer. Okay. So are we clear so far when it comes to forming a relation or set relation?
Yes, sir.
Yes, sir.
All right. So again, the first thing that you need to look at is this arrangement of your coordinates. So x first, followed by the y, and then whatever is the second condition, wherein we have here y divided by x having a 0 remainder. All right. So let's now move on to the example number 3. So we have here set x where it has an element of 1, 2, 3, 4, and then addition are defined by x, y. Okay. So if x is less than or equal to y, and x, y is an element of x. Okay. So as you can see right here, we only have one set, but we have a condition here that our here we have a condition here wherein our x coordinate and then y coordinate will be coming from our x or set x. Okay, so those two are an element under set x. Okay, so it could be 1, 1, 1, 2, 1, 3, 1, 4, and so on and so forth. Okay, so what is our next condition is 1. So x should be less than or equal to y. Okay, so actually you can use Cartesian product in here. Okay, since all of your coordinates will be coming from one set. So let me just copy this one. And then paste it right here. So we have this condition, x should be less than or equal to y. Okay, so let's write those relations. Okay, so from here we could say 1, 1,
1, 1,
2,
2.
1, 1, 2.
No, 1, 2, 1, 3,
Mhm,
1, 4.
mhm. What else?
2, 2, 2,
2, 2,
2,
and
3,
2, 3.
2, 4,
Okay, and then
3, 3,
3. Okay, very good. And
3, 4, 3, 4,
what else?
4, 4.
4, 4.
All right. So as you can see, super easy when it comes to forming a relation. As long as you know on how to solve or analyze this rules or condition, then you're good to go. Okay. So in here we have a total 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 sets of binary relations. Okay. All right, so let's move on to the next example. So in here, draw the relation or using the digraph. Okay, so first, when we see digraph, okay, this one is a connection or a relation between two elements. Okay, so from this to this point. Okay, so let me show on how to answer this one or draw those relations using a digraph. So this one is super easy. So as you can see right here, we have a relation 1, 1, blah, 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 and so on and so forth. So this one is actually the answer from past example, the one that we just answered. So if we have 1, 1, then you can answer this one as this one. So as you can see, we have 1, 2, 3, 4 elements. So we have 1, 1, oops, 1, 1. Okay. So 1 will just go back to itself. Okay. And then we have 1, 2. Okay, so 1 going to 2, oops, yeah, and then 1 going to 3, and then 1 going to 4, and then 2, 2. So again, it will just go back to itself, and then 2, 3, and then 2, 4. Then we have here 3, 3, and then we have here 3, 4. Oops. Then we have 4, 4. Okay. So this is now the representation of this set relation into a digraph or digraph. Okay. So did you get it so far?
Yes, sir.
Yes, sir.
All right. So this one is super easy to follow. Just know the coordinates of those. All right. So let's have another example. So draw the relation R on X having an element of A, B, C, D defined by R, AA, BC, CB, DB. Okay. So it says here draw. So we should come up with a digraph or digraph. Okay. Let me just copy this one. All right. So from here we have elements A, B, C, and D. So oops. So we have A, B, C, and then D. And then we have this relations. We have AA. Then we have BC. Then we have CB. Then we have DB. Okay. So this is now the digraph representation of this relation. All right. So very simple. All right, so once you're done in understanding everything, all of those from page 1, slide 1 to slide 12, then you may now start in answering this sequence number 2. Okay, so we have letter A, letter B, and then letter C. So for letter A, draw the digraph of the relation. So just the same in this one or similar. Okay, and then for letter B, write the relation as a set of ordered pairs. Okay, so you should come up the same with letter A as a result. Okay, given with this diagram. And then letter C, the relation R on the set 1, 2, 3, 4, 5 defined by the rule x, y is an element of R. And then we have three conditions. Okay,
Sir,
so you, yes,
the letter B of B has no relations. How do we write that as other pairs? BB.
this one.
Yes.
So since there is no, this one should be your assignment. Okay, so as you can see, there is no relation. Okay, so I'll just give this one as a bonus. Then just list that as no element or an empty set. Okay, since there is no relation. Okay. So did you get this one now?
Yes, sir. Thank you.
All right. Okay, so again, for the seat work number 1 up to the end of the seat work of this module, so you can do it handwritten or you can do it via Microsoft Word. Okay, so please, if you're going to do it handwritten, please write legibly. Okay, and then from here, you have additional tasks to do. So you have to identify the elements of R of this letter A, then the domain of R, and then the range of R. Okay, so do not just get the ordered pairs. Okay, so get the elements and then the domain and then the range. So the same with B and letters. Okay,
Either.
all right. So let's now move on to the next one. So we have here properties of relations. So we have here reflexive, symmetric, transitive, and then anti-symmetric. Okay. So for reflexive, so as you can see, it reflects itself. So if we have one element, then it should also reflect itself or its own element. So let's say we have 1, 2, 3 elements. So the only time that you could say that it's reflexive if we have 1, 1, 2, 2, and then 3, 3 ordered pairs. Okay, so this one is super simple, reflexive. Then we have here symmetric. So you can say that it's symmetric if for all x, y is an element of x such that x, y is an element of R, then yx is also an element of R. Meaning, if we have this kind of ordered pairs, let's say 1, 2, then you should also have 2, 1. All right. So if you have, let's say 2, 3, you should also have 3, 2. Okay. So they are now symmetrical. Okay. So it's like mirrored. Okay. So this one is also super simple. And then transitive. So this one is also super simple, which came from hypothetical syllogism. You can still recall this one on the induction. So we have here x, y as an element of R, and then y, z as an element of R. And then imply x, z is an element of R. Meaning, once you have find out that you have this kind of ordered pair, we have x, y, and then y, z, wherein they have the same element for this one, y, and then y in here, then you can come up with an x, z, or another ordered pair. So once you saw this one, x, z, okay, in this ordered pair, then you can see that they are transitive. But if there is one element that doesn't have this x, z, then that is not transitive anymore. Okay. Anyway, so we're going to have more examples for this one later on so that you guys will understand this one more. Okay, and then we have this anti-symmetric. So as you can see, this one is completely the opposite of symmetric. So if this one is not symmetric anymore, okay, let's say we have xy but we don't have yx, okay, then that one is already anti-symmetric. Okay, so as simple as that. All right, so let's start with the reflexive relation. So as I mentioned a while ago, if we have this elements 1, 2, 3, 4, then you should have 1, 1, 2, 2, 3, 3, and then 4, 4. Okay, you can just disregard the others. As long as you have those, then you can say that this relation is reflexive. Okay, so yeah, the question is a relation reflexive. So relation R is reflexive because each element x is an element of x, xx is an element of R. So specifically the 1, 1, 2, 2, 3, 3, and then 4, 4. So did you guys get this one so far?
Yes, sir.
Yes, sir.
Okay, so this one's very straightforward. If it's reflexive, it should reflect its own element. Okay. All right, so we have here another example. So let R AA, BC, CB, and then DB. So is this relation reflexive?
Yes, sir.
Yes, sir.
Huh?
Yes, sir.
What are the elements on our relation?
AABD.
AADD.
AA, BB only?
A, B, C, D.
A, B, C, D. That's it. So take note, we have here an elements of A, A, B, C, and then D. Okay. And then for you to be able to see that this one is reflexive, if we have AA, BB, CC, and then DD, right? Is this
Yes.
correct?
Yes, sir. Yes, sir.
This, for us to say that this one is reflexive. But how about this example? Is this reflexive or no?
Sir, oh, I actually thought we can actually just, so far some of the elements are reflexive. Because that's what I thought. That's what I said it.
No. Okay. So when we say reflexive, all of the elements should reflect itself. Okay. It's not
Okay.
suffice that there is only one element that reflects itself. Okay. So yes, it is true that for some it is reflexive, but for all it is not reflexive. Okay, wherein the condition of reflexive is it should be all. Okay, everything. Okay, as you can see right here, we have 1, 2, 3, 4. 1, 1 has its own reflection to itself. 2, 2 has its own. 3, 3 has its own, and then 4, 4 has its own also. But in here, we don't have the BB and then the CC. Okay, so that is why this relation is not totally reflexive or not reflexive at all. All right.
Okay, sir. Okay.
So I hope this one is clear. When we say reflexive, all of the elements should reflect itself. All right, so since we don't have enough time anymore, so we will just continue the remaining slides on the part 2. Okay, so I will end this meeting now, and then I will create a new link or a new room again, and then just join right away. So right now we have 17, or we are 17 participants, so I'm expecting the same participants also. All right. So before we end, do you guys have a question?
Wala naman po, sir.
Oh, sir.
All right. So let just wait for the second link. Goodbye. Okay. So can you guys see my screen now?
Sir. Yes, sir.
All right. Okay. So the next one here is digraph on reflexive relation. Okay. So here's just the representation of a digraph. Well, as you can see, if we have 4 elements, we also have 4 reflexive ordered pairs. So we have 1, 1, 2, 2, 3, 3, and then 4, 4. If we have 2, then we also have 2. AA and then BB. All right. Then we also have symmetric relation. Okay, so again, when we see symmetric relation, if we have the ordered pair x, y, then we should also have an ordered pair y, x. Okay, so we have this example. Let R is equal to AA, BC, CB, and then DB. So in here, relation R is symmetric. Okay, so let me just explain why. So as you can see, if we have x, y, we should also have yx, right? And in here we have variable a as your x, and then another a as your y for AA. And then if you're going to come up with its yx, it is still the same, okay? Which is still, which is still AA. So that is why if it's reflexive ordered pair, then it is also already a symmetric ordered pair. All right, so are we clear on that? So this one is already considered as symmetric ordered pair. So did you guys understand that one? Hello? You guys still listening?
So I don't understand. You said if it is reflexive, then it is symmetric.
Yeah, as long as you have this condition. If you have this ordered pair, then you must also have this ordered pair. And your x here is A, your y here is also A. And if you're going to have a yx, it's still AA, which
Yeah, I
is
understand for this particular example. But for the first example, that is not symmetric because some of them are not like
yeah,
that.
that what example is that?
The first example, this one, yeah.
This one?
For 1, 1, 2, 2, the other one.
This one is actually symmetric also.
No, not for this one. There's another one down there.
This one?
Yeah, this example 2.
We're not there yet. Okay? We're still in example number 1. So as you can see, we already have an answer which is not symmetric. Okay, we were still in example number 1, which is this one. Okay, I'm just explaining it step by step on why this AA is already reflexive and then symmetric at the same time. Okay, which is just this one. Okay, and as you can see, for this second ordered pair, we have BC, then we should also have CB. Okay, so this is our X, this is our Y. So just interchange those. We have YX, which is your C, and then BB. Okay, wherein we also have that one in our list of ordered pairs. So we have BC, which is this one, and then we also have CB. Okay, and then this BB is the same with this concept. All right. So simple as that. If you have X, Y, you should also have YX. Did you guys get it so far?
Yes, sir.
Yes, sir.
All right. So this one's very straightforward. Anyway, let's move on to example number 2. So as you can see, 1, 1. So no problem. But how about 1, 2? Okay. So you should check this one already. So if you have 1, 2, you should also already have 2, 1. Okay. Wherein it cannot be found. Okay. It's missing on our list. So that is why this one is not already symmetric. Okay. If there is one ordered pair that doesn't or wasn't able to follow this rule or condition, then that one is not asymmetric anymore. Okay, so you could say that this one is anti-symmetric relation already. Okay, so one ordered pair is already enough. Okay, so you don't need to check everything. Okay, so did you guys get the example number 2?
Yes, sir.
Sir.
All right, so
Yes,
let's
sir.
move on to the digraph on symmetric relation. So the digraph of a symmetric relation has a directed variable or element v to w and a directed edge w to v. Okay, so it should be vice versa. Okay, so AA and then BB, no problem. I have already explained that one using this one. And then for CB and then BC, so as you can see, if C will go to B, there should be also B going to C. Okay, so it will go back or it mirrored itself. Okay, so the same with this example. If we have so 1, 1, 2, 2, 3, 3, and 4, 4, so no problem on those. But for 2, 1, oops, 1, 2, no. Okay, so this one is not symmetric. So this one actually is the example number 2. Okay, and then this diagram is the example number 1. Okay. So this is just the representation of a diagram. So as you can see right here, we have 1, 4, but there is no line that is going back to the 1 or 4 going to the 1. Okay. So that is why this diagram is not a symmetric relation, right? So are we clear so far on a symmetric relation?
Yes, sir.
Yes,
All right,
sir.
so let's now move on to the anti-symmetric relation. So this one is super easy since we already learned about symmetric relation. So again, we have 1, 1, so no problem. But we have here 1, 2, wherein it doesn't have 2, 1 as another ordered pair. So if that's the case, then this one is already anti-symmetric. So this one is actually the same example with this one. So before we just call that one not symmetric because I haven't introduced anti-symmetric yet. But since you already know anti-symmetric, then just call this one anti-symmetric. Okay. So for example number 2, we have here AA, BC, CB, and then DB. So you could see that this one is not anti-symmetric because this one is symmetric. Okay. So are we clear so far? For the
Yes,
example
sir.
number 2. How about the others?
Yes, sir.
Clear naman, sir.
All right. So here's the continuation of anti-symmetric relation. So tell whether the following relations are anti-symmetric or no. Okay. So letter A, is this anti-symmetric or not?
Anti, sir.
So this one is anti-symmetric because first of all, it doesn't have a relation to compare with. Okay. So if you have 1, 1, let's say 1, 2, then that's already good. Okay, this one is already anti-symmetric, but since we don't have those ordered pair, the x and then the y, then this one is not anti-symmetric, or this one is anti-symmetric rather. Okay. How about letter B? Is this anti-symmetric or symmetric?
Not anti-symmetric.
Okay, not,
Symmetric.
so not anti-symmetric or symmetric. So they are just the same. How about letter C?
Anti-symmetric.
Asymmetric.
Symmetric po.
This one is anti-symmetric because as you can see right here, we have 1, 2, but we don't have 2, 1. Right, so this one is anti-symmetric. Right, so are we clear so far regarding with anti-symmetric relation?
Yes, sir.
All right, so I hope the others can also follow. Okay, let's now move on to the transitive relation. Okay, so this one is super easy to understand. So let me just copy this one. Just place it here. This one is very helpful. Okay, so as you can see right here, if we have x, y, and then y, z, okay, we should also have an ordered pair x, z. Okay, so the same with hypothetical syllogism. Okay, so let's take a look on this example number 1. So we have here 1, 1, and then 1, 2. And as you can see, so as you can see, we have here the x, y, and then the y, z. Okay, so y is the same as 1, which is 1, 1. Then we should also have an x, z. Okay, so you have to find this x, z, which is 1, 2. Okay, so this 1, 2 is the same with this one. Okay, oops. Well, this is only coincidence for this example. Okay, so then as you can see, we're good for this part. We could say that for 1, 1, and 1, 2, it's transitive. But how about the others? So let's check. So we have 1, 3, 1, 4, 2, 2, 2, 3. Right here. So we have 1, 1, and 1, 3. Okay. So we have the x, y, and then we have the y, z for the y3. So x, y, and then y, z. Oops, y, z. Okay, so again, you should have this x, z, which is 1, 3, which can also be found on this ordered pair, which is a 1, 3. Okay, so this one is also good as a transitive relation. What else? This 1, 1, and 1, 4. So as you can see, we should have this 1 and then 4, which can also be found on its ordered pair, which is 1, 4. So we are good up to this point also. Okay, let's check the others. What about 1, 2, and then 2, 2? Okay, so we have x, y, and then y, z. So as you can see, we also have this 1, 2 already. Okay, so x, z is 1, 2, which is this one already. So can you guys follow on how we check step by step this relation as a transitive relation?
Yes, sir.
Yes.
Sir.
All right, so again, if we have this x, y, and then y, z, you should come up with another ordered pair, which is called the x, z. Okay, so I would like you guys to verify the remaining ordered pair, whether they are really a reflexive or a complete transitive, rather, not reflexive, complete transitive relation. So your hint here is actually the last part and then the first part of the ordered pair. So you guys have to check this part, 1, 1, 1, 1 again for 1, 3, and then 1, 1 again for 1, 4, and then 1, 2 for the 2, 2 right here, and then 2, 2 for the 2, 3, and then 2, 2 for the 2, 4, 1, 2 for the 2, 4, 1, 2 for the 2, 3. So you have to check all of those. Okay. So you should arrive with x, z ordered pair. Okay. Or there should be an ordered pair x, z on this relation. So have you guys checked everything already? Almost.
Yes, sir.
All right, to those who are not yet done, so I'll give this one as your self-study assignment, okay, or self-study example rather. Okay, so this one is transitive, okay? So if you have x, y, and then y, z, you should have x, z, okay? How about example number 2? So as you can see right here, we have BC, and then we have CB. Let me just copy this one. All right, so we have BC as your x, oops, xy, and then we have CB as your yz. Okay, so again, we should have another ordered pair, which is the xz, wherein in here it will form a BB. Okay, an ordered pair BB. So is this BB on this relation or set relation? No, guys.
No,
Okay,
sir.
fine.
Wala po.
So, no, right? So this one is not transitive already. Okay. So as long as you can find one ordered pair wherein it wasn't able to apply the transitive rule, then this one is not transitive anymore. Right? So are we clear so far with this transitive relation? Any concerns or questions or clarification up to this point?
Wala naman po, sir.
All right. Okay, so let's now move on to the examples. So consider the relation less than or equal on this set N. So is the relation reflexive? So let me just put this one. Oops. Where's this one first? Okay, so in here we have a relation x is less than or equal with y. Okay, wherein this one is under an element of natural numbers. Okay, so what are the elements of natural numbers again? Where do we start?
1, 1.
Natural numbers. Is it
Starts from
0 or 1?
0, sir.
Okay, so we will start with 0. So 0, 1, 2, and then 3. So we'll just get this limitation. So 0, 1, 2, and 3. So 4 elements only. And then we have this condition. X is less than or equal to y. Okay. So since
Sir,
right
di ba
here, if you're going-
natural numbers?
yes?
Sir, di ba natural numbers? E di
Yes.
maunang 1, sir.
Check nga. Na-miss out ko
Sir,
eh,
yes,
kasi
mauna po yung 1. Nakalagay.
so there's no 0.
Yes, sir. Full numbers na
Alright.
po kung may 0, sir.
I see. Sorry for that one. So if it's z plus or integer positive, so 1 and above. But if it's full number, then that's the time that you will include 0. But in natural numbers, it's the same with z plus. You will start with 1 and above. Okay, so we'll just take 1, 2, and 3. So since right here we have this condition. So if you're going to follow this one, if we have this elements for the ordered pair, x, y is an element of natural numbers. So you can form a relation. 1, 1, 1, 2, 1, 3, and then 2, 2, and then 2, 3. and then 3, 3. Okay. So as you can see, we have 1, 2, and 3. So for you to be able to say that this one is reflexive, so we should have 1, 1, 2, 2, and then 3, 3 on this relation, which is correct because we have 1, 1, we have 2, 2, and then we have 3. So that is why this relation under this condition is reflexive. Right? So did you guys get it so far
Yes, sir.
on why this relation is reflexive?
Yes, sir.
Okay, so how about the question, is the relation transitive? Okay, let's say we have still the same relations. We have this 1, 2, 3, 6 elements. I mean 6 ordered pair, not elements. Let me just remove the circles. So is this transitive or no?
Transitive.
So this one is also transitive because as you can see right here, we have 1, 1, 1, 2. We also have 1, 2. Okay, 1, 1. I mean 1, 2. This one first. 1, 1, 1, 1, and then 1, 3. We also have 1, 1, 2, and then 2, 2. We also have 1, 2. 1, 2, and then 2, 3. We also have 1, 3. And then 1, 3, and then 3, 3. We also have 1, 3. And then 2, 3, and then 3, 3. We also have 2, 3. Okay. So as you can see, just check every possible ordered pair when it comes to checking transitive. Then you must have that x, z on that relation. Okay. So this one is transitive. How about the next one? So we have another condition here. Consider the relation less than on the set n. So is the relation symmetric? So as you can see, this one is not symmetric anymore because we will never arrive at 3, 3, and then 4, 4. Right? Since we have this condition, or we have to follow this condition. Okay. Oops. That one is for reflexive. Sorry, this one is symmetric. Okay. So you will never get a 4, 3 rather. Sorry. You will never have a 4, 3 condition because your first ordered pair or first coordinate is always lesser than the second coordinate. Okay. So are we good so far for this symmetric?
So
All right.
Yes,
How
sir.
about the last one? Anti-symmetric. Okay. So as you can see, same condition, same example, or same elements. Okay. So if it's not symmetric, then as usual, this one is already anti-symmetric. Okay, because we will never arrive at 4, 3. Okay. All right. So I hope those examples are super clear on you guys. So let's now move on to the order relations. So we have two parts under order relations. So we have partial order and then the equivalence order. So for now, we'll talk about partial order. So when we see partial order, so this is an order or a condition wherein it met the certain relation wherein it should be reflexive, it should be anti-symmetric, and then transitive at the same time. Okay, if there is one relation that is not met on a particular, say, example, then that one is not already a partial order. Okay, so you should have these three condition or these three relations. Okay, reflexive, anti-symmetric, and then transitive. So for you to be able to say that this one is partial order, just say
Nasa
right.
mo walay sa computer.
So you can actually, oops. So you can actually just say if this one is partial order, then it should be equal with RAT. Okay. So what is this RAT? So it's reflexive, anti-symmetric, and then transitive. Okay, so I just come up with this RAT for you to have an easier way of memorizing the conditions or the relations. Okay, R for reflexive, A for anti-symmetric, and then P for transitive. All right, so let's have an example. So prove that the relation R defined on the Z plus. Okay, so Z plus again is 1 and above by this condition, X divides Y, wherein you will have a result of even, okay, is a partial order. So we should check whether this relation or partial set relation is really a partial order. All right, so let me just copy this one. So again, we'll just use 3 elements for the Z plus. Okay, so this one is positive integer. So we'll just get 1, 2, and 3. And then here's our second condition. So we have here X divides Y. Again, this one is Y divided by X. Okay, wherein you should get an even result, or in other words, you should not have a remainder. Okay. All right. So let's check what are the relations under this condition. So 1, 2, is it a relation regarding with this condition?
Can we start from 1, 1?
Yeah, so yes, sorry. So 1, 1. So we can start with 1, 1. So as you can see, this one is already even. How about 1, 2?
1, 2.
So is this part of the relation? This 1, 2?
Yes.
So yes, because again, just follow this condition. So we have 2 divided by 1, which is equal to even, which is 2. Okay. How about 1, 3?
Yes.
Yes, sir.
Also, how about 2, 1?
No.
Okay.
No, sir.
No, because again, that will become 1 over 2. Okay. How about 2, 2?
Yes, sir.
Yes, sir.
Yes. How about 2, 3?
No, sir.
No, sir.
No. How about 3, 1?
No, sir.
Oh, 3, 2?
No.
All right. How about 3, 3?
Yes.
All right. So we have now formed the uh, relation set under this condition. All right. So all we need to do is check whether this one is reflexive. So again, RAT, reflexive, anti-symmetric, and then transitive. So is this relation reflexive?
Yes.
So yes. How about anti-symmetric? Is this anti-symmetric?
No, sir. Symmetric.
No. No.
So this one is symmetric.
Yes.
Yes, sir.
How come that this one is symmetric? So again, if we have xy, we should also have yz, right? If it's symmetric. But in here, we have 1, 2, but we don't have 2, 1.
No. We have 1, 2. And we have 2, 2.
Yeah,
And that will give us 1.
but we don't have 2, 1. Yz. Yx rather.
Yeah, yx. X, Y, Y, Z. Then we should have XZ.
No. That one is for transitive. What I'm asking is the
Oh.
anti-symmetric.
Oh, anti-symmetric. Yes, anti-symmetric.
All right. So this one is anti-symmetric because we don't have 2, 1. Okay. We have 1, 2, but we don't have 2, 1. We have 1, 3, but we don't have 3, 1. All right. How about
Yes.
transitive?
Yes,
So yes,
transitive.
also. Okay. We have 1, 1, 1, 2. We also have 1, 2. Okay. What else? 1, 2, and then 2, 2. We also have 1, 2, which is this one. Okay. So as you can see, this one is a partial order. So if all of those are yes, then you could say that this one is partial order. Right? Okay, so are we clear so far when it comes to checking on this particular relation?
Yes, sir.
Okay, so just memorize those 3: reflexive, anti-symmetric, and then transitive. If there is at least one, let's say it's not transitive, this one is not a partial order anymore. Okay, so all of those should be a yes, right? So again, once you're done in understanding all of the past topics that we have just discussed, then you may now proceed in answering the seat work number 3. So here you're going to determine whether its relation defined on the set of positive integers is reflexive, symmetric, anti-symmetric, transitive, and or partial order. Okay, so you have to indicate whether this one is symmetric. If it's symmetric, then just put there symmetric. If it's reflexive, then just put the reflexive. And then again, if it's reflexive, anti-symmetric, and then transitive, then just put their partial order. Okay?
Or multiple choice yan.
No. Okay, so you will do this one using Microsoft Word or handwritten. Okay, so I want you guys to show the same as like what I did on the past example. This one. Okay, so you have to list all of the possible elements and then the possible ordered pairs or relation set. Okay, and then we have those conditions. All right. So are we clear so far?
Yes, sir.
All right. So
Yes,
let's move
sir.
on to the order relations. Okay. So suppose that R is a partial order on a set X. So if X and Y is an element of X and either X is less than or equal to Y or Y is less than or equal to X, then X and Y are comparable. Okay. Then vice versa, if we don't have that condition, X, Y, and then YX, then that one is incomparable. Okay. So if every pair of elements in X is comparable, then R is a total order. Okay, so meaning if you have this XY, then you should have YX. Okay, if you don't have one of those, then that one is already not a total order. Well, this one is super easy to understand. Again, just take note on this condition. XY, you should have YX. So this one is actually the same with symmetric. So if it's symmetric, then that one is a total order. Okay. And then we have here the inverse of relation, wherein it's denoted by R raised to -1. Okay. So this one is actually super simple. Okay. If we have 2, 4, you must also have 4, 2. Okay. If you have 2, 6, you must also have 6, 2. And then you have 3, 3, you must also have 3, 3, you should say. 3, 6, you should also have 6, 3, and then 4, 4, 4, 4. Okay, so basically, and it's asking you to have an inverse of relation or R raised to -1. You just have to, interchange the X to Y and then Y to X, which is the same with this example. Okay, so the same with letter B. We have BC, we have CB. We have CB, we have BC. Okay. So are we clear so far regarding with inverse of relation?
Yes, sir.
Yes, sir.
All right. So we will stop here again for now since we don't have enough time. We'll just continue the rest on the part 3. Okay. All right, so let us now continue our discussion. So before we continue, do you guys have a concern or clarification? Hello?
No, sir.
Any question or concern before we continue?
None, sir.
All right. So if there is no question, then let's now continue. Okay. So we have here the inverse of relation using a digraph. Okay. So this is the original digraph. Okay. And then this is the inverse relation of a digraph. Okay. So we have 1A, 1B, 2A, 2B, 2C, which is this one. And then the inverse of that one is the A1, B1, A2, B2, and then C2. So as you can see, our x coordinate became the y coordinate, and then our y coordinate became our x coordinate. Okay, so our domain became the range, range became the domain. Okay, so simple as that. Then you're good to go. All right, so are we clear so far regarding with this digraph?
Yes, sir.
How about the others? Or is it that only Mr. Maaba and Mr. Palawewa that I'm hearing to respond? Okay, so let me just check. Miss Rona Ramos? All right, so no response. So I guess she's not around. How about Mark Jason?
None, sir.
Okay, Mr. Kabuwag?
None, sir.
Okay, Mr. Gangas?
Gets naman, sir.
All right, how about Mr. Paran?
Wala din naman sir.
All right, how about Mr. Estalivia?
Gets none, sir.
Mr. Tanikala?
Gets naman, sir.
Okay, about Miss Grace? Miss Grace Ginran?
Gets, sir.
Okay, how about Miss Sekdigan?
Gets po, sir.
Okay, about Mr. Agustin?
Gets, sir.
Mr. Mendoza? So maybe she's not around. I mean, he's not around. How about Mr. Mark Jason?
Sir, it's naman po.
Okay, how about Mr. Alukan?
Gets po, sir.
All right. And then Mr. Kabuwag, I think I have already called you.
Sir.
All right. So again, if you guys have a question or any concern, so feel free to ask me or let me know your concern. Okay. So once you're done with those statics, then you may now start in answering the seat break number 4. Okay. So the relation R and the set 1, 2, 3, 4, 5 defined by the rule x, y is an element of R. Okay. So get all of the list of ordered pair. Okay. And then find, or for each relation, find the inverse relation. Okay. So I should see two answer, the ordered pair and then the inverse relation of that ordered pair. Okay. So next one is composition of relation. So we have here O as a representation for composition. Okay, so it is denoted by R2. O R1 is the relation from X to Z defined by this kind of formula. So we have R2 O R1, wherein we have XY or XZ as your element for R1, and then we have YW or ZW as your element for the R2. Then you should arrive at XW. Okay. All right, so let's have this example. We have the R1 and then the R2. So the question here is, what is R2 O R1? So just simply apply this formula and then you will get this answer. So from here, as you can see, we have 1, 2, and then 2U. Okay. So this one is actually quite similar with the implication or hypothetical syllogism or the transitive. So if we have 1, 2, and then 2U, you should have 1U. Okay. But instead of, in part of that relation, it is now in a form of R2 O R1. Okay. So you will come up with another relation. Okay. So this one now is your composition of relation of R2 over R1. Okay. So if you have 1, 2, and then 2U, you have 1U. What else? If you have 1, 6, and 60, you should have 1T. Or you will get 1T. What else? You have 2, 4, and then 4S, you will get 2S. Okay, you have 2, 4, and then 4T, you will get 2T. Then what else? For 3, 4, and then 3, 3, 4, and then 4S, you will get 3S. 3, 4, and then 4T, you will get 3T. And then T6, and then 60, you will get 3T. And then 3, 8, and then 8U, you will get 3U. Okay, so how did we come up with those ordered pair? So from this formula, which is the XW. Okay, so if you have XY and then YW, you should have XW. Okay, if you have XZ and then ZW, you should have ZW. Okay, so let me just include it here. ZW. All right. So are we clear so
Sir?
far?
I
Yes.
don't understand. XZ and ZW. That should also give us XW.
What? This one? X, Z, and
ZW.
ZW. Okay.
That should give us XW also.
XW. Yeah. Sorry. Thank you for that one, Mr. Palawewa. So this one is still the same. XW. XW. Yeah. Okay. So that is where I didn't include another one. So just this one, XW. XW. Yeah. Right. So did you guys get this one? Are we clear? Or is there a part that it's confusing you?
Clear, yes, sir.
Clear, sir.
All right. So again, when we say composition, you need two relations, and then just have this formula or apply this formula, then you will come up with XW or with this kind of answer. Okay. So once you're done with that topic, you're going to have, of course, a short safe break or activity. So we have here the R1 and then the R2. Okay, and then you should have the list of the element of R1O R2 and R2O R1. All right. So moving on, we have here the equivalence relation, okay, or the another type of order, call this one, order relation. So before we have the partial order, wherein we have the RAT, which is reflexive, anti-symmetric, and then transitive. But right now, we have the equivalence relation, wherein it is reflexive, but it is now symmetric instead of anti-symmetric, and it's still transitive. So for partial order, it is RAT or RAT, But for equivalence relation, we have here the RST, right? So those are their only difference. So same process. So you'll be given a set of relations, and then just check whether that one is reflexive, symmetric, and then transitive. If all of those three were able to met the condition, then you could say that this one is an equivalence relation. All right. So here's the solution for this example. We have the 1, 1 up to 4, 4. Okay, so as you can see, we have checked one by one. So this one is reflexive. Yes, we have 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6. And then this one is also symmetric because we have 1, 3, 3, 1, 1, 5, 5, 1, and so on and so forth. Okay, and then this one also is transitive because we have the 1, 1, 1, 3, and we have the 1, 3, which is this one. Okay, so just check everything on all of those. Okay, transitive, symmetric, and then reflexive. If all of those are checked, then that one is an equivalence relation. Okay, so we will not discuss this one by one anymore because this one is quite similar with the partial order. It's just that instead of this one anti-symmetric, this one will become symmetric. Okay, so are we clear so far regarding with equivalence relation?
Yes, sir.
Yes, sir.
Yes po.
All right. Okay,
Yes,
so
sir.
that's good that some of you are now starting to respond. So once you're done with that example, okay, or partial order and equivalence relation example, so you may now start and answer this seat work number 6. So all to do is tell which of the following relations are equivalence relation or as equivalence relation. Okay, so again, when say equivalence, it's reflexive, symmetric, and then transitive. So we have 4 numbers for this one, right? And then recall set partition. So a collection S of non-empty subsets of X is said to be partition of the set X if every element in X belongs to exactly one member of S. Okay. So as you can see right here, we have an X having an elements of 1, 2, 3, 4, 5, 6, 7, 8. And then if this one has a one member under one set, okay, which is the same with this one. So we have 1, 4, 5, 2, 6, 3, and then 7, 8. And then as you can see, this one is under one set from this set. Then we could say that this set is a partition of that set. Okay, so you can see that S is a partition of X. Okay, well, the point in here is if you have this class, class, then all of them should be under one set, or should all of their elements should be found on the superset or this set X. Okay. So if you're going to take a look on this one is just with the use of what is one part, yeah, Cartesian product. Okay, on every set. So we have 1, 1, we have 1, 4, we have 1, 5, we have 4, 4, we have 4, 1, 4, 4 only, and then we have 4, 5, and then we have 5, 5, and we have 4, 1, sorry. So it's just that we are shuffled. So we have 4, 1, and then we also have 5, 1, which is this one. Okay, and then we have 5, 4, and then 5, 5, of course. So as you can see, this one is the Cartesian product of itself. Okay, so if you're going to get the total numbers, okay, or total list of ordered pair, so just multiply it to itself. So 3 times 3, so you will get a total of 9 elements for this one, and then 2 times 2, so you will get a total of 4 elements for this one, and then 1 times 1 is still 1, and then 2 times 2 is 4. And then if you're going to add all of those, so 9 plus 4 is 13, plus 1 is 14, plus 2, plus 4 is 18, am I correct? 14 plus 4, 18. 9, 4 plus 4, 17, 18. Yeah, 18. So let's see if we have a total of 18 ordered pair. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So all of those came from this set, okay, with the use of Cartesian product, right? Anyway, so this is just to say that this one is under a set of partition or under a superset. Okay, so this one is a partition of that superset. Okay, so let's have another example for you to appreciate this one. So using a digraph, we have this 1, 3, 5, we have this 2, 6, and then we have this 4, right? So as you can see, using Cartesian product, you will have this reflexive, symmetric, and is it transitive? Transitive. If we have 3, 5, 3, 3. Yeah, it is also transitive. Okay. So anyway, once you have this list of elements, then you can now draw this one. Okay, so this is the digraph of this class 135, and then this is the digraph of this class, which is the 2, 6, and then we have this digraph of this 4, which is coming from the superset 1, 2, 3, 4, 5, 6. Right? So this is just a recall because we're going to use this one later on. Okay, what is this class, this class, this class, and then this class? Okay, so let's move on with equivalence class, wherein our very main topic regarding with this set partition. So let R be an equivalence relation on a set X. So the sets A defined in set partition. So what is our set partition again? So this is an example of set partition. So where this one came from? This one came from our superset, which is this X. So for equivalence class, okay, so we will list all of the possible elements, okay, or all of the let's say student. Okay, so under class we have students. So we have this certain class 135, and then it has a student of 3 elements, or the 1, 3, and 5. And then for the second class we have 2, 6, and then of course it has a student of 2, which is the 2 and 6. And for the last one, under one class we only have one student, so we only have 1, 4. So 1, 3, 5, 2, 6, and then 4. So in this set partition, we have a total of 3 class, okay? And then each of them have a student, okay? Wherein this one has 3, has 2, and then has 1. So maybe right now you're quite confused on how we apply this equivalence class. So let's have another example. Okay, so given the following relation, R is equal to AA, BB, and then CC. So write the equivalence classes. Okay. So as you can see, this one is very obvious. Okay, so this is one class, another class, and then another class. Okay, so under this class, we have one element only, which is the A. Okay, and then another class wherein we have one element also, which is B, and then another class which is same element or same number of elements, which is one only, which is C. So second question is, how many equivalence classes are there in relation or in this relation? So you can say 3, since we have only formed 3 classes. Okay. So classes are divided by or this one separated by a comma. Okay. So just like this, we have 3 class in total. So can you guys follow now, at least a little, when it comes to classes?
Medyo
Yes.
So,
Yes, sir.
All right. So at least need 50% of your understanding. So it's okay if you only understand 50%. Okay, so let's have another example. So how many equivalence classes are there in the following relation? So we have this relation. Okay, so all we need to do is check how many relations are there in, or how many classes rather, not relation. How many classes are there in this relation? Okay, so listen carefully on this one. Okay, so from here we have to check all of the distinct elements. Okay, so as you can see right here, we have one. Oops. We have one. We have two. We have three. We also have four. And then lastly, we have five. Okay. All right. So as you can see right here, we have 1, 1. So which is now this one. Okay. One element on that class. And then we also have 1, 3. So we could say that this one is a classmate of 3. Okay. So they are classmate under one class. Okay. And then what else? 1 is also related with 5. Okay, so we could say that 1 is also a classmate to element 5. What else? 1, 1, 1, 3, 1, 5. What about 1, 4? Do we have 1, 4? Okay, none. So as you can see right here, this is already one class, okay, having an elements of 1, 3, and then 5. Did I use the correct? Yeah, it's a curly bracket. All right. So this is already one class, 1, 3, and 5. Okay, because we have just find out that the classmates of 1 is 3 and then 5. Okay, so they are just under one class. How about 2? So 2 is also related with 3, so they are in the same class. How about 4? Yes, so they are also related in one class. 2, 4. What about 1? So we don't have 2, 1. So it doesn't matter what is the arrangement. So we can have 2, 4 or 4, 2. Okay, so they are just C. So as you can see right here, we have 2, 4, and then we have 4, 2. So you don't need to list the 4 or 2 here again. Okay, so you only need 1. Okay, so meaning they are related with each other already. Okay, how about 2, 5? Do we have 2, 5? Okay, so I guess none. Okay, so this is already one class having a set of our elements of 2, 3, and then 4. Oops, 3D bracket. And then for 3, so 3 is related with 1, 3 is also related with 5, and 3 is also related with 2. So 2 and 1. Oops. And then 5. What else? We have 3, 4. Okay, so we don't have 3, 4. So this is again another class. Okay, wherein we have 2, 1, 5. Okay, you have a question, Mr. Palawewa?
What about 3?
3? Sorry. 3 and then 5. Yeah. So thank you so much, Mr. Palawewa, for filling up my call this one missing information or lack of information. All right, so how about 4? 4 is related with 4, which is one already. 4 is related with 2. And 4, we have 4, 1. We have 4, 5. So none. So from here, we could say that this is again another class wherein we only have two elements, which is 4 and then 2. Okay, how about 5? So 5 is related with 3. 5 is also related with 1. What else? Do we have 5, 2?
That's it.
5, 4, 9. Okay. That's it. So from here, this is again another class which is composed of element 5, 3, and 1. All right. So check everything. Okay. So it seems that everything is okay already. So once you're done in creating, okay, or coming up with the list of elements on every class, then you have to check whether there are the same classes. So as you can see right here, we have this one and this one. So they are just the same. And then again, since this one is a set, so arrangement doesn't matter. Okay. So the next question here is, or the question here is, how many equivalence classes are there in the following relation? So as you can see, this is one class, another class, and then another class. But in here, we can eliminate the another one already since we already have this one. So we only have a total of 1, 2, 3, 4 classes. 4 classes. So that's how we identify on how many classes are there in the following relations. So did you guys get this one so far?
Yes, sir.
Yes, sir.
Yes.
Yes, sir.
Look, just look for the relations, okay, on each of ordered pair, and then make a list of it as a class like this one, and then check whether there is similar or the same elements. Then count how many classes we have in total. So in here we have a total of 4 classes. All right. How about example letter B? So we have here x 1 to 10, and then define x related to y if 3 divides x minus y. Okay, y here is already given, so we only have 1, 2, 3 as our y. And then as you can see, the numbers of x is 10, 7, 4, and 1 for this class. Okay, because that one is the condition that were met under this condition. So 10 minus 1 is 9, divided by 3 is a whole number. So 3 divided by 3 is 1. So 7 minus 1 is 6. So 6 divided by 3 is 2. And then 4 minus 1 is 3. So 3 divided by 3 is 1. And then 1 minus 1 is 0. So 0 divided by 3 is 0, okay, which is still a whole number. So as you can see right here, we just get the list of x under this condition. So the same with this one, list of x under this condition, and then list of x under this condition. So in total, we have come up with 3 classes. Okay. So 1 for 7, 10, 2, 5, 8, and then 3, 6, 9. So this is one class, another class, and then another class. Right? So are we clear so far regarding with this equivalence classes?
Yes, sir.
Yes, sir.
All right then. So again, you're going to have a seat work, of course. So we have this. So supposedly this one is letter A, and then this one's letter B, and then C. Or you can just ignore that one. Okay, just arrange that one using their alphabetical letters. So we have here A, B, C, D, E, F, G, and then A, B, C, D, E again. Okay, so just follow their order with alphabetical order. Okay, so for this one, determine whether the given relation is an equivalence relation on 1, 2, 3, 4, 5. So if the relation is an equivalence relation, list equivalence classes. Okay, so you should verify this one, whether this one is a relation under equivalence relation. Then if it's an equivalence relation, then list all the possible classes or list equivalence classes. Okay. So the same with B, C, and D. And then for this one, determine whether the given relation is an equivalence relation on 1, 2, 3, 4, 5. So if the relation equivalence is an equivalence, so this, yeah, they are just the same. Okay, but in here, since this one is already given as a relation or ordered pair relation, this one is not yet. So you're going to analyze this one first, the same with this one, letter B, and then come up with the list of relations and then its equivalence classes. So in here, it's like double steps or double solutions. Okay, so we have 4 numbers for this one. And for the last one is the members of the equivalence relations on 1, 2, 3, 4. Also find the equivalence classes of 1, 2, 3, and 4. Okay, so this one is the easiest part on this activity, since you know, all you have to do is list the members of equivalence relations. So just like what we did on this one. Okay, so any questions so far regarding with your seat work number 7?
Wala naman, sir.
Answer.
All right, so let's now move on to the next one, matrices. So this is already the last topic for this module. So matrices of relations. So a matrix is a convenient way to represent a relation from R from X to Y used by computer to analyze a relation. So we have here the row for the X and then Y or column for the Y. Okay. So if the set or if the entry on that X and Y is in relation with each other, or X is related to Y, then just put there 1. If they are not related with each other, or if they don't have any relation, then just put there 0. Okay, so let's have an example. So given the relation 1B, 1B, 2C3, C3B, 4A, and then we have these coordinates from X, 1, 2, 3, 4, from Y, we have A, B, C, D. So relative to the orderings 1, 2, 3, 4, and then A, B, C, D. So take note, your X here is the 1, 2, 3, 4, which is the rows. And then the Y here is the column, which is an arrangement of A, B, C, D, okay, which is this one. Okay, so just be wary when it comes to putting the format or arrangement. So for the column, it is the Y, and then for the rows, it is the X. Okay, so since right here we have 1B. So again, just look on the 1B coordinates and then just put there 1. So we have 1B, wherein they are in relation with each other. So just make this one 1. And then we have 1B. So just make this 1. And then we have 2C. So just make this 1 also. And then we have 3C. And then 3B. And then 4A. And then no more. Okay, so that's it. So for you to have an easier way of doing this one, so you can just leave the entire matrix blank for now, and then plot the relations, okay, or the ordered pair wherein they are in relation. So make this one 1, 1, 1, 1, 1, and then once you're done in doing that one, then you can now fill up the rest by 0. Okay, so that's how we plot a relation or an ordered pair using a matrix relations or matrices of relations. So did you guys get this one so far?
Yes, sir.
Yes, sir.
All right. So again, we don't have enough time anymore. So We'll just continue the rest, so don't worry. It's now only 11 slides, so it maybe will only take 10 minutes more or less. So we'll just continue the rest on the part 4. Okay. So again, goodbye for now, and then just wait for the link of the part 4. This module 4. Okay. So any other questions so far with this example number 1? Hello? Can you guys hear me?
Yes, sir. Gets naman po.
Yes, sir. A question.
Sure. All right. So next example, I have this ordered pair or relation, and then we have this arrangement 1, 2, 3, 4, A, B, C, and D. But when it comes to orderings in matrices, so just be wary on this one. So as you can see right here, we have 2, 3, 4, 1 for your rows, and then D, B, A, C for your column. Okay. So 2, 3, 4, 1, D, B, A, C. Okay. So look for 1B. So we have here 1 and then B. So just make this one 1. And then we have here 1D. So which is now this one, 1D. And then 2C, which is this one. And then 3C, which is this one. And then 3B, which is again this one. And then 4A is this one. So as you can see, plotting the corresponding arrangement on matrices is easy, but the one thing that you need to be wary is the 2, 3, 4, 1 for the arrangement or the orderings of this relative ordered pair. Okay, it's the same with Y, which is DBAC. So that is why we have the note here: the matrix of a relation from X to Y is dependent on the orderings of X and Y. Okay. Did you guys get this one so far?
Yes, sir. Gets naman po.
Okay, so similar example, but just a different orderings. All right, so let's have another example. So write the matrix of the relation R from 2, 3, 4 to 5, 6, 7, 8. Okay, so relative to the orderings 2, 3, 4, and then 5, 6, 7, 8. So yeah, we don't have a problem when it comes to orderings, which is the same. But then you have to follow this condition for us to come up with a certain list of relations, wherein X is related to Y if X divides Y. Again, this X divides Y is Y divided by X, wherein we'll have a zero remainder, or we'll have a result of even number. Right, so let's see. So Y is 5, 6, 7, 8. So 5, 2. So 5, 2 is a no-no. 5, 3 is a no-no. 5, 4 is a no-no also. But in 6, 2 and then 6, 3, then that's a time that they are now in relation with each other. Correct? 6, 2 and 6, 3.
Yes, sir. 6, 2, 6,
6
3.
divided by 2 is even, and then 6 divided by 3 is also even. So that is why you have to plot here 1 and then 1. 6, 2 and then 6, 3. How about 7, 2? No. 7, 3? No. 7,
No.
4? No. But for the 8, so
8,
8,
4.
2 and 8, 4. Okay. So 8, 2, and then 8,
And
4.
8, 4.
Okay. So did you guys understand example number 3?
Sir.
Yes,
All right.
sir.
Okay. Very good. Again, if you guys have a question, so feel free to ask me anytime. Okay, so let us now move on to the example number 4. So write the matrix of the relation AA, BB, CC, DD, BC, and then CB on ABCD relative to the ordering A, B, C, and D. So no problem when it comes to ordering. So ABCD and then ABCD. So we have here the AA, BB, CC, CB, CC, and then D. So as you can see right here, this one is reflexive, having one line for the AA, BB, CC, and then DB. And then this one is also, call this one symmetric, okay? Because we have BC and then we have C. Okay. So understood when it comes to example number 4?
Yes, sir.
Okay. And is this transitive? BC, CB, B. No, this one is not transitive. So this one is only reflexive and then symmetric. All right. So with the use of those examples, so I hope you were able to understand what is matrix all about. So once you're done understanding all of those, then you may now proceed and answering this seat break number 8. Okay. So find the matrix of the relation R from X to Y relative to the given orderings. So the orderings are already given in here, and then we have here the relations. So I need you guys to plot this one, so you should come up with this kind of answer for 1, 2, 3, and then 4 and 5. Okay. And for 6, 7, 8, so it's the opposite. Okay. So you should come up with the relation R, okay, which is similar with this one. All right. So I'll give you guys 10 seconds to take a look on your seat break number 8, and then just let me know if you have a clarification. Right. So any concerns so far regarding with your seat break number 8?
Wala naman po, sir.
How about the others?
Wala po,
Yes,
sir.
sir.
All right. Okay, let's now move on to the next one. We have here the representation on a matrix of reflexive properties. As you can see, we have AA, BB, CC, and then DD. So this one is a relation R is reflexive if and only if the matrix has ones on the main diagonal. So this is the main diagonal. Okay. And we also have symmetric property if we have this kind of representation on the matrix. So we have BC and then we have CB. Okay. So let's now move on to the matrix multiplication. So let R1 be the relation from 1, 2, 3 to Y, AB, and define as R1 is 1A, 2B, 3A, 3B. Okay. So this one is just a random relation that came from these sets. Okay. And then we have another relation. So let R to be the relation from Y to Z, wherein Z is equal to X, Y, Z defined by R2, AX, AY, BY, and then BZ. Okay. So here's the matrix representation of your R1. And then here's the matrix representation of your R2. Okay. So we have 1A, 2B, 3A, and then 3B. And then we have AX, AY, BY, and then BZ for this one. Now, the question here is we have to multiply R1 to R2 or R1 times R2. Okay, so here's the solution. Okay, so here's the R1 and then here's the R2. And then here's the product of the matrix from R1 to R2. Okay, so how did we come up with this one? Okay, so let me just copy this one and then show it step by step on this paint. So the first thing that you need to check here is the size of your matrix. Okay, so in our R1, we have here a 3 by 2 matrix. Oops. 3 by 2 matrix. So 3 is your row, and then 2 is your column. So as you can see, we have 3 rows and then 2 columns. So this is the size of your R1. And then for the R2, what is the size of R2?
2 by 3.
2 by 3. Okay. So as you can see right here, we have 2 rows and then 3 columns. Okay. This is now the size of your R2. All right. So the question here is we have to multiply the R1 to your R2. But before you can do that, there is one thing that you need to check. Okay. So let me just erase this one. All right. So from here, you have to check the size of your column from the first relation or first matrix to the row of the second matrix. So those two should be equal with each other. Okay. So if they are not equal, then you won't be able to get the product of those two matrices. Okay. So from here we have the same two columns and then two rows. Okay. So if it's checked, then you can now proceed in getting the product of those two relations. So how will you know what is the size of the product from those two relations or from those two matrices? So all you do is multiply the row of the first matrix to the column of the second matrix. So as you can see, 3 times 3 is equal to 9. Okay, or 3 by 3, or the size of your product is 3 by 3, which is now this one. So 3 rows and then 3 columns. So did you guys get this one so far?
Yes,
Yes,
sir.
sir.
All right. So
Yes.
next one is the computation. Okay, so how did we come up with this 1, 1, 1, 1, 1, 2, 1? Okay, so here's the process. So you have to multiply this row to this column. Okay, so 1 times 1 is 1 plus 0 times 0 is 0. So 1 plus 0 is equal to 1. Okay, which is now this one. Okay, how about the second or the second one, which is under y? So the same process. So the row from your first matrix and the column on your second matrix. So just multiply this one to this. So 1 times 1 is 1. And then 0 times 1 is 0, which is still 1. Okay, so 1 plus 0 is equal 1, which is now this 1. And then for the third one, so just multiply this row to the last column. Okay, so this 1 to this 0. So 1 times 0 is 0, plus 0 times 1 is still 0. So 0 plus 0 is 0, which is now this one. Okay, so can you guys follow so far?
Yes,
Yes, sir.
sir.
Yes, sir.
Okay, so if you want to solve for the second column of the product, so use this one instead. So multiply this to the first column, and then you will get this one. Multiply this second row to the second column, then you will get this one. And then this one to the third column, then you will get this one. So the same with the third row. Okay, so multiply this one to get multiply this one here to get this one, and then this to the second column to get the second column, and then this to the last column to get the last column. Last column, last row. Okay, so I will leave the second row and then third row as your, as your self-study example. Okay, and how did we come up with those? All right. So let's say we have already computed everything and then come up with this result. Okay. So the next one here is the composite relation R2O R1. Well, this one is super simple. Once you saw a 1, okay, or a non-zero term, so no matter what is the number or the value of that certain row and column, so just change that 1 into 1. Okay, so as you can see right here, we have 2 here, but when it comes to R2O R1 or composite relation, that 1 will become 1. So if we have, let's say, 25, 30, 36, 80, 1000, so all of those non-zero term will just become 1. Okay, which is now this one. So did you guys get the matrix multiplication so far and the composite relation?
Yes, sir.
Yes, sir.
All right. So once you're done in those topics, then you may now proceed and answer seat break number 9. So this is already the last one. So I apologize for giving a lot of activities since we already lag behind when it comes to the target time for our modules. All right, so you have 9 seat breaks for this module 4. So it is already in your canvas. So just check that one and then just do it one by one. Then of course, do it as of now or starting now. Okay, so that's it for your module 4. So don't you guys have a question?
Wala naman po, sir.
All right, so if you guys do not have a question anymore, then you guys may now go. And then thank you for coming.
Thank you.
Thank you, sir.
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 Thank you, sir.